So let's have a look at this now. So we're saying that the rate constant is concentration of Q, you said? Concentration of R squared.
Yes, sir, which is 0.02.
So what's our, okay, so let me scroll up a little bit up here. So we can see the rate. So the rate is 1.2 times 10. That 10 looks weird. Times 10 to the power of negative 4. Right, and all we're going to be doing now is just dividing it by, wait, is that the one you're looking at? Okay, that's the one that we have to look at. 0.02 squared. This is 0.02 squared.
Yes, sir.
So plug that in into your calculators and see what comes out. What are our answers now?
2.4 times 10 to the minus 6.
15.
Okay, so we're clearly seeing that there's some issues here. So somebody get 2.4 times 10 to the minus 6, so somebody get 15. What is the answer? What is the true answer?
15.
Oh, sorry. Okay, let me fix this. Let me fix
Sir, you're
this.
missing a 0.02.
I should be. I should put a cube. Sorry about that. Cube it. Because I put cube. I cubed it, no, but I forgot to write it here. So what is the answer when you cube it? The answer should be 15.
Cube what?
The denominator. It's on this. Are we seeing the screen? I wrote the 3 on the screen.
Jay,
Go ahead.
what were you referring to be cubed?
I was referring to the denominator.
0.02.
0.02.
Why is it supposed to be cubed?
Okay. Because
Because it's a second order reaction.
okay, because it's a second order reaction and well, what? No, no, not necessarily, not necessarily. Right? We have this as r squared, right? And we see that q is the same value, so we're
Because
just going to
there's
cube
three
it.
of them.
It's 3 of them, so that's what I'm gonna do.
Oh, okay. I see it now.
Okay. That's why I cube it. What is the unit of k here? What's the unit of the rate constant k? So if rate is mole, mole per dm negative
So it's
3.
more square. So would it be per mole square dm to the 6?
Yes,
Per second.
per second.
Yes.
Alright. So we're going to cancel out and then we're gonna get, as you said, per mole squared dm to the sixth power, positive sixth power.
So mole per um,
And then that sixth power up here where I have minus, well not minus, well to s to the minus 1. So I have that. Complete the table by inserting the missing values of q and r. and the initial rate for the reactions between Q and R. Now, for this though, let me just check something real quick. Are we supposed to be doing a graph? No, we aren't. Okay. So to be very honest, in the interest of time, I'm going to ask, do you guys know how to calculate these? Because you now have the rate constant k. All you do, you plug in your k, and then you find here x, 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 and x. Plug it into the equation, and then go around to find answers, right? Okay.
Wait, sir.
What
Sir,
happened?
could you go? Sir, how do you?
Wait,
Sir, go over that.
no, sir. Can you?
Okay. So let's say for experiment 2, we need to find the rate, right? Remember the equation. It's this equation we're going to be using, right? For equation 2, we don't know the rate. So look at the equation above. We call the rate x, and then we just plug in the rest of the values to find the rate, and you just plug that answer there. So what I'm saying is that for each missing value, all you do is call each variable x, transpose the equation, and you find the answer. That makes sense?
Oh, okay. Yeah,
Okay.
that makes sense.
So probably because the x thing that I did with the table never made no sense. But yeah. So you guys should be getting values for that. So in the interest of time, that's just math. It's not chemistry, so that's just fine. Right? The order of reaction with respect to R is 2. State the meaning of the term order of reaction with respect to R. So what does order of reaction mean?
The coefficient by which the reactant is raised by.
I mean, yes, it's a coefficient the coefficient by which well, it's the exponent by which the the concentration of R is raised by. So
It's the relationship between the concentration and the rate.
alright. So it's a relationship between the concentration rate. So it's the dependence, right? It's the dependence of the rate on the concentration of the reactant, right? So not only it is that exponent that is raised, that the power that the it's not the only the exponent that the concentration of R is raised to, right? But it is the power dependence, what we call the power dependence, right? Of the rate of R, not the rate of reaction, right? On the concentration of R. So it's a relationship between the two, right? So what I'm gonna put in bracket under here is what we've said first. So the exponent by which the concentration of R is raised to, right? So generally that. So what these are basically saying the same thing. It generally means the same thing. Alright? So we'll have a look at that. Deduce the overall 1 plus 2 is what? 3? Alright, moving on. Oh, 1 plus 1 plus 3 is 3. Interesting. 1 plus 2 is 3. So all we do is add the orders of reaction. Alright? Everybody understand how we get these two? 3 and 4? Alright, I think this thumbs up. Alright.
Yes, sir.
A fixed mass of marble lumps is reacted with dilute hydrochloric acid at a constant temperature. Outline why the rate of reaction would increase if the lumps of marble are reduced in size. So raise hand and go ahead.
I would say the rate of reaction would increase because the surface area is increasing, so more reactions would occur. So yeah.
Yes, sir. There would be more particles to react with, and the particles would be more exposed.
All right. So somebody raise their hand. Go ahead. Somebody raise their hand. Not sure. All right. So what we have here, we know that the rate of the reaction will increase in proportion with the increase of surface area, as there are more possible areas of collision. Right. So there are more areas of collision because we cut the molecule, not the molecule, the marble lump so much. There, it's spread out. So there are more specific areas, right, on the marble that the hydrochloric acid can collide with and react, right? So that is what's happening there. Okay, moving on. Oh my, skip too far. When a 0.218 mole of sample, well, mole sample of hydrogen iodide was heated in the flask with volume V, right? The following equilibrium is established at 700 Kelvin. The equilibrium mixture was found to contain 0.02 moles of hydrogen. Calculate the number of moles of iodine and the number of moles of hydrogen iodide in the equilibrium mixture. How many moles of hydrogen are present?
Um, 0.023.
Oh, sorry. Yeah. Okay. Okay. So we know that 0.023 is present, right? So 0.023 here, 0.023. Right. So calculate the number of moles of iodine and the number of moles of hydrogen iodide. So what would you do in the number of moles of iodine? What would be the answer? Go ahead.
Um, would it also be 0.023?
Okay, that's interesting. Zach, would it also be 0.023?
Yes, sir.
All right. Zamora, will it also be 0.023?
Yes, sir.
0.023. All right. Moving on. What would be the number of moles of hydrogen iodide now? Because probably within this question, what we're asked to do is to use an ice table to find the answer. Right? Because that is the thing that we explore in Unit 1 to get Unit 1 students to get to learn how to use an ice table. So I believe that that would be the more suitable answer for this question. All right. And if we do that here now, let me just check to see if this is the right answer. 0.172, and then we're going to add now. Yes, this is the right answer. So if you want to check whether or not your answer is right for these stuff, right? It's in this type of scenario, right, where one amount of moles is producing the entire equilibrium, just add it up. If you add up and it's not the same answer, not same amount of moles rather, then the answer would be wrong. Right? Does that make sense?
Sir, could you go back to the ice table thing, please? I was trying to follow, but kind of get lost.
All right, give me one moment. Sorry, 0. So for the ice table, what we're saying now? So what we're saying is that with an ice table, we're saying that we initially started, right, with 0.218, right, of our hydrogen iodide. Yeah, and then what we have up here now is going to be plus X hydrogen and X iodine. We don't know, right? So what we're saying that is the concentration, right? Or technically it's going to be the pressure. But oh well. So we're seeing the concentration here, right? Of this will create our concentration X here and our concentration X here. So it must come from that. Meaning that while these two values increase by whatever value, right? That will be minusing, or that will be subtracting from the original number of moles, because what we're seeing is that the hydrogen iodide is decomposing, so the original number of moles is decreasing and becoming hydrogen gas concentration, hydrogen iodide concentration, not hydrogen gas concentration and iodine concentration. That's what I'm saying, right? So the x's are coming from this. So whatever amount the products increase by will be the amount the reactants decrease by. And because of the mole ratio being 2 to 1 for those, we minus 2 of the 2x, right? So 2 of the amount that the products will increase by. And then we're supposed to be able to get that answer there. So since we know what x is now, we're gonna be minusing 2 times that x, right, from the original number of moles to get the actual number of moles of hydrogen iodide that exists at equilibrium. All right. So I think this is a paper that bothered me somewhat, because we're not supposed to be really writing a Kc, right, for this reaction. We're supposed to be technically writing a Kp because they're gaseous, but they ask us to write a Kc expression. So we're going to write the Kc expression that they ask us to write. And what will be the answer here? What would be the answer for the Kc?
Um, 0.179.
Okay, everybody.
0.0179.
Okay, 0.0179. Okay. Everybody else got the same general answer, 0.017. So 18. Okay, 179. What are the units of Kc here? Are there any units?
No, sir, I don't think there are any units.
Alright.
Usually cancel out.
Yeah, they should usually cancel out.
So
Okay, is it not? Does Kc always cancel out? No. If the bottom wasn't squared, it wouldn't cancel out. Right, but the bottom is squared.
no, it doesn't always.
Alright, lovely. So calculate the Kc of this reaction now. The reverse. What would be the Kc of the reverse? So that Kc, let me just write it out.
Just flip it, sir. React into a product instead.
So what we do is flip, right?
Yes, sir.
Okay, so we flip it. So what we have is 0.023 squared. 0.023 squared. And then on top we have 0.172 squared. And what's going to be our answer?
$55.92.
Okay, Zach, go ahead.
Sir, I got the same answer, 55.92, sir. But what I did was I did 1 upon the answer that we got before, because it was actually just the inverse.
Okay, yeah, it would be the inverse. So it's just flipping the fraction, it would be the inverse. Okay. All right. D. Buffer solutions are necessary in a wide range of applications ranging from biological systems to industrial processes. State the meaning of the term buffer solution.
So can you scroll up for a second, please?
Okay, let me scroll up. While I scroll up, somebody can tell what a buffer solution is.
Sir, buffer solution is a solution that resists drastic changes in pH when adding small amounts of base or acid.
Lovely. Right? That's what a buffer
Oh
solution
yeah.
is. Go ahead.
Can you scroll up to the first part of the question?
Scroll back down now. Can move now?
Yes, sir.
All right.
Yeah.
Zach, go ahead. You have a question?
Sir, did you go through any solubility product question as yet, sir? I went away for a while, so
Yes, we
I'm
did
not
quite a
sure.
few. But we're going to be going through the past papers with them. So no problem.
Sir, can I see the question above, please?
Which question? This question, the buffer systems one? This one?
No,
The one above this?
no, sir. The yes, sir. Yes, sir.
Okay, okay. So we know that a buffer is a solution that would resist any drastic change in pH when small amounts of acid or base are added, right? And that's generally the definition that we have for that one down there. Go ahead. Somebody raise their hand.
Sir, I have a question.
Go ahead.
For the last part of the question, why did you flip the KC?
We flip the KC because we're doing the reverse reaction, which would be the product now upon, which would be this, which was our reactant, now upon this, which was our product. So we just switch it. It's reverse. That's why. So we just flip them.
Okay, thank you.
All right. Now, what we're called to do is to identify a reagent which could be added to the solution of ammonia in order to form our solution. What's a reagent that could be added to ammonia to form that?
Ammonia chloride.
Ammonium chloride, lovely. So NH ammonia chloride, ammonium chloride. All right, lovely. Consider the following equation, which represents a buffer solution consisting of a weak acid and its conjugate base. Explain the effect on the buffer solution if the concentration of hydrogen ions and hydroxide ions increase separately. So it's just many fancy ways of asking the same thing that has been occurring for 4 separate years now, right? What happened when acid added? What happened when hydrogen ions get added? Acid added and hydroxide added. What's happening? When the acid is happening, what's happening?
When the acid is added, it would react with the base, and when the base is added, it would react with the acid.
Alright, so when the acid is added to the base,
Yeah.
we're going to have the movement of the equilibrium. Wait. Alright, so when we add it to the base, right? What we're doing is decreasing the concentration of here, right? So the equilibrium will eventually push this way. And then if we're reacting the base, what we're doing is decreasing the concentration of this, so our reactant will actually go this way. Alright, So that is that. Yes, why it's not moving. Explain how the molecular
So with the
structure.
hydrogen ions equilibrium,
Well, the same thing with hydrogen ions.
sir.
If we say that the hydronium or hydroxonium ion equilibrium will, if we say that that concentration will increase, right? What we're going to have is the reaction being pushed over, right? And then that would actually have to be reestablished. So what's going to happen here? If the hydroxonium ions will increase, we have to shift the equilibrium to the left, right? Wait, if hydroxyl ion increase, okay, let's not think of the equilibrium like that. What's gonna
Sir,
happen is that that this base is going to consume the extra hydroxyl. Go ahead.
sir, I was just confused as to the arrows. I was wondering, when the acid is added, when the hydrogen ions are added, the equilibrium will shift to the left, right?
We'll shift to the. Okay, hold on. What's the question?
So that's the question because I wasn't hearing well, and the arrows, I'm not sure what direction that's pointing to.
Okay.
So I'm asking.
So with the acid, right? If the extra ions are gonna be added, our salt is going to be
Hydrogen
consuming that.
ions.
Mhm. Our salt is gonna be consuming that, right? And what's gonna happen with the hydrogen ions, right, is that after we decrease the concentration of our salt here, what we're going to be doing is shifting the equilibrium to counteract that decrease to produce more of our salt. That's what's happening there, right? And with our acid here now, if our acid has OH applied to it now, so the OH is applied to it now, it's neutralizing the OH. That hydrogen goes to neutralize to form water, right? What's gonna happen here is that we're decreasing the concentration of our acid, right? Well, we're decreasing the concentration of our acid we're decreasing the concentration of our acid, right?
Sir,
So go ahead.
this is a buffer.
Yes.
Sir, isn't it that the hydrogen ions would react with the conjugate base, and the equilibrium will shift to the left
Decrease the hydrogen.
to maintain the pH? So the hydrogen ions, the excess ones that are added, will be used up by the conjugate base, and equilibrium will shift to the left.
All right, hold on. Let's look at this. All right. Let's have a look at this. All right. So let me. Oh, I can't do that. Could I? Is there another one? No, there's no other one. All right. So hopefully my cursor is switched. All right. When hydrogen ion to the concentration, our base is going to accept that, right? Okay, let me explain it from a different perspective. Let me use it from the perspective that I've been using from morning, right? So we had hydrogen ions here, right? Right? Coming in. Lovely, right? That would actually increase the amount of acid that we have, right? And that will shift equilibrium to the right. Does that make sense? Because what we're doing, if we're adding that now, what we're increasing the amount of our acid in our solution, right? And we're gonna shift the equilibrium over here in order to actually regain our amount of salt here, right? So what's gonna happen here is that our salt concentration is gonna be
Okay, sir.
decreasing.
Now you're saying.
Okay, because our salt concentration is gonna be decreasing, right? So what we need to do is shift to counteract the change. Because after we accept it now, right?
Excuse
What
me,
we're going to
sir.
go ahead.
Sir, I don't know if this will make sense, but if you add if you increase the concentration of the hydrogen ions, it will react with the conjugate base and it will increase the acidity. So the equilibrium would shift to the left. That makes sense?
So,
Uh-huh.
and the H, the concentration of the H would decrease by doing that.
Okay, hold on. So,
Okay.
okay.
Alright.
So, what we're doing when we react with protons here, right? We're reacting with the protons here. We're taking this with us, right? So that concentration is going to be increased. We're moving that, right? So what's going to happen to the equilibrium? We're moving that concentration. What's going to happen to the equilibrium?
It shifts to the right to restore the conjugate base.
Okay, does that make sense to people?
Yes, sir.
Yes, sir.
Alright, so that makes sense. We should to the right here. Right? The thing is no, right? What's happening specifically is that we're gonna have the creation of more acid, right? And it's a weak acid in the presence of water, right? So it's going to ionize naturally. So what we're having is a specific pH. So the pH is caused, right, by our conjugate base, right, and our conjugate acid. What will happen is that our base is going to be used up in neutralizing, right? So technically what's going to happen is that the pH will increase for a second, right? And now the base will be used up in neutralizing specifically, right? So the concentration of base will actually decrease as well, right? Overall. And then what we're gonna have to do now is push the equilibrium to restore the concentration of A. And if we have hydroxides reacting now, we're going to actually react with our acid, right? And we're gonna have an increase the concentration of A. So if we increase the concentration of A, the equilibrium will move to the left to decrease the concentration of A, right? And each time we react, we're going to have the replenishing of our salt and the replenishing of our acid, right? Because that's how the buffer would actually maintain its entire pH. It has to replenish salt concentration, it has to replenish, salt concentration and its entire acid concentration. Okay? And explain how the molecular structure of amino acids relates to their function as buffers in the human body. How would we do that? So we know that amino acids specifically have different groups on them. So all you have to do is explain that in one scenario one, if there's a lot of acid being added, here can accept it. And in scenario two, if there's a lot of OH being added, right, this can neutralize it, right? So with that information, you should be able to answer this question. All right. How much marks is this question?
Wait, sir, you're explaining it in terms of like the diagram, but to explain it in words now.
Oh, okay. That's why we
Like the
know what.
diagram makes sense,
But you see this error right here?
the diagram
Wait,
makes sense, but to put it into words,
Jay,
Go ahead.
is it a case wherein if you add hydroxide, if you add hydrogen, it will bond with the amine group, and if you add hydroxide, it will react with the hydrogen from there to form water?
Yes. So it stabilizes pH like that, right? But what's happening here, right? You see all that space I just put a rectangle there? All that space is your space, right? So it's your space on the paper to write this diagram and refer to it. You can draw diagrams and refer to it. So what this diagram is saying is that amino acids naturally contain, right, a carboxylic acid group and a amine group. In water in natural conditions, they form Zwitter ions, right? And the Zwitter ions allows us or exemplifies the fact that the amino acid can actually gain a proton to its amine group, right, in order to reduce hydrogen ion concentration in a solution, or it can actually lose hydrogen from its carboxylic acid group to neutralize hydroxide into water, right? So it has two possibilities. So
Sir?
with the amino acids, right? Go ahead.
Is that how it normally works, or is that isn't it the zwitter ion in the blood? So like in solution, you would refer to how it works as the zwitter ion, not just the amino acid molecule. So the zwitter ion is already polar.
Mm-hmm.
So you have the carboxylic acid, the COO minus, and the amine group is the NH3 plus, right?
All right.
So when the
Go ahead.
hydrogen ion concentration increases, wouldn't it bind with the carboxyl group to use up the excess acid?
All right. So that's what will happen, right? So
Oh,
explaining that now.
I thought you were saying something different. Sorry.
No, it's fine. I just haven't reached there, right? So what's happening here is that within water specifically, right, we're going to have this bonding. So basically, right, if it is in a basic solution, right, specifically if we want to maintain an alkali solution, it can neutralize acid. If it's going to be in a acidic solution, it can neutralize the base, right? So generally when it exists as a sweeter ion, as you were saying, right, we could actually have the release of protons, right, to neutralize the base, and the acceptance of protons, right, to neutralize acids, right? So it can work in both regards necessarily, right, as an amino acid. And somewhere has our hand up, so go ahead.
Yes, sir. So you're saying that the amine group within the amino acid accepts the hydrogen, and what the carboxyl part accepts the hydroxide, and that's how it
Well,
works as the buffer.
it loses hydrogen, it loses a proton. Because remember, acids donate protons. So the carboxylic acid part donates protons to hydroxide to form water, right? So when it does that, what we're going to do is having bonds form, and we're going to have a positive area here, and we're going to have, when the hydrogen leaves, we're going to have a negative part here, right? So it exists as a Zwitter ion, right, when we have that type of structure. And when it is in the blood, right, because it is a Zwitter ion, it can either accept hydroxide or neutralize an acid. Well, not accept hydroxide, accept a proton or neutralize a base, right? So it has both of those capabilities. Go ahead.
Amine group will have a +1 charge when it accepts the proton.
Yes, it will. And the carboxylate area would actually have a negative charge, right? So what's happening here now, in laboratory exercises, students are asked to determine the pH of a buffer made by the addition of measured quantities of ethanoic acid and sodium ethanoate. Identify two relevant pieces of apparatus that would use to, well, student apparatus or materials that may have been used by the students to carry out the experiment. What could we do for that? This is literally the repeat of a question from 2015, I believe. Literally the repeat. I don't think the concepts have changed. It's literally the same question, right? So, have a go at this. Right, because earlier I would have mentioned that a pH meter is the best and most accurate tool to use, right? And if we use a pH meter, right, what we'll generally need to use is two solutions of buffers for calibration. So we can call them the calibration solutions. And they can be buffer solutions. Right.
Is there solutions?
We can use solutions to calibrate the pH. But if you can't use the pH meter, you can actually go through a titration, in which a pipette is useful and a volumetric flask is useful. Because there are different approaches. Or indicator could be one as well. And a material indicator. Right? That can be used. Alright, so there are multiple ways to do that. You can do via titration, or you can use potentiometry, which is basically using your pH meter. Alright, identify 2 relevant experimental steps taken by the students, determine the pH of the buffer. 2 key or 2 relevant experimental steps, what would those be? So in the case of the calibration of the pipette, calibrating it is important. So calibration would be one. Right, another thing for the pipette would be doing what? Experimental steps. Now for the pipette, the pH meter. Right, you would calibrate a pipette as well. But you can calibrate the pH meter, right? And if you're using pH meter, what could you do after? 2 experimental steps. What's another step?
How do you do this experiment?
Bye-bye.
Alright, we could speak about how we do the experiment, but let's just complete the question first. You calibrate and then what? Nobody in this entire meeting has done the experiment? Or knows how to do it, or has heard of using a pH meter in order to do the...
So I haven't used a pH meter or calibration solutions. We only know it through titrations.
Yes.
Sir, I used the pH meter, but it wasn't like calibrated or anything. We used titration with the pH meter.
Okay, you could use titration with the pH meter. Okay, that's what you guys... Okay. Alright, so if you're doing a titration, then what are the 2 experimental steps that you would use then? Doing a titration, since that is what is familiar, go ahead.
Sir, adding indicator.
So adding suitable indicator. So what else? What's another key experimental step for the titration? I will that titration is the more famous one. So any other step that you do for titration?
Sir, use the pipette to measure a volume of
25 cm3. That's what we're saying.
Sir?
Repeat what you're saying. I never heard you.
So I was saying you could use the pipette to measure the volume of one of the reagents.
Okay. So the use of the pipette though, I'm not sure. Okay. 2 relevant steps, right? The thing is that the use of accurate.
Sir, when taking the pH to keep the pH meter away from the bottom of the flask.
Right, hold on for titration, right? We're holding with titration, right? So what he's talking about is the use of accurate measuring instruments. That's what he's talking about, right? But probably a little bit more safer one would probably be like conditioning the instruments. What am I doing? The instruments. Conditioning instruments could be a very interesting, very important thing to do, because when we're working with buffer pHs, we don't want any external solutions or any type of contamination to affect, right? Here, no calibration, right? Maintaining the position of the meter, and we tend to use something like a retort stand and clamp And this is so that the retard, retard stand and clamp, right? So we tend to do that because we want the pH meter to be submerged in solution, but not touching anything. So it just needs to be submerged in solution at all times, and it needs to be within a solution at all times. So we make sure that the bulb doesn't dry out, right? For that. And I think that is the rest of the entire question there. And then you move on to module 3.